Hello everyone, welcome to my channel Hypermesh Basic to Advanced. In this video, we will see how to optimize components in Hypermesh. So first things first, what do we mean by optimization? Optimization means to modify something such that it can be used to its best potential with minimum penalties. So suppose in a case we have a component like this bracket which will be subject to some non-loading conditions. Okay. So if the loading conditions are known, then we can modify the design of this bracket. Okay. So what modifications can we do? We can remove or add the materials. We can increase or reduce the volume of the bracket, and all these modifications can be done such that the functionalities of this bracket is not affected. Okay. So where is this optimization used? Okay. So this type of optimization basically comes handy where we have weight, area, or some volume constraints. Okay. So optimization helps in modifying the design to better fit with these constraints. So apart from this, it can also help to reduce the manufacturing cost of products. Suppose if we can remove some material or we can reduce the volume of this uh, bracket, then the manufacturing cost, the material which goes into manufacturing this would be less. So we will save on cost. Okay. So in this tutorial, we are going to optimize the design of this bracket using Optistruct. So the very first step would be to divide this bracket into design and non-design regions. Okay. So why are we dividing the bracket into design and non-design regions? Okay. So this is to prevent the modification of the interfacing areas. So what are the interfacing areas? So as you can see here, the load is applied on these two holes here. If I zoom a bit, okay. So you can see the load is applied on these two holes and constraints are placed on these four holes. Okay. So suppose if we don't divide the bracket into design and non-design areas, then what will happen during optimization? When optimization is going on, it might remove some material from these holes also, which might be a problem because these holes are the holes which will interface with other components for transferring the constraints and the loads to this bracket. Okay. So how do we divide this component into design and non-design area? So we can do that by going to geometry. We can go to solid edit. Okay, and then we can divide the geometry into design and non-design area. Okay, so once dividing it into design and non-design area, we have to mesh the model. I've already meshed the model, as you can see here. I've used tetra elements with size 2 for meshing the model. Okay, post that I've used RB2 elements for creating a calculated node for applying constraints on these four holes on the flat face of the bracket, and RB2 elements for applying load on this two holes on the projected face of the bracket. So I have applied a load of 3000 Newton in the negative y direction. Okay. So this is the basic boundary condition under which the bracket will be operated. Okay. So this is the basic setup for any analysis or optimization which we need to do first. Okay. Then I have created a material. I have used the same material as steel, which is a default material available in Hypermesh. Okay. After that, I have created properties. So here I have created two properties. One is design property and one is non-design property. So design property is for the design component and non-design property is for the non-design component. Okay. So after creating the meshed model and creating the material, creating the property, and then assigning the property to this design and non-design component, we can proceed to create optimization variables. Okay. So after this, before that, we also have to apply the loading conditions. Okay, I've created a constraint load collector and load axial load force of 3000 Newton in the negative y direction, as you can see here in the white browser area. Okay, and after that I have created a static analysis load step here. Okay, in which I have referenced this constraint under the SPC field and load under the load field. Okay, so to optimize this bracket design, we have to go to analysis and to optimization. Okay, so suppose this optimization is not visible here, you can go to preferences here and you can go to user profiles, and then you can select the user profile there as Optistruct. Then it will come here. Okay, so this is here. So we'll go to analysis, optimization, and then we'll click on optimization. So what we are basically doing here is that topology optimization. So what is topology optimization is? Topology is basically we modify the mass, weight, area, volume of the component. Okay, and then we also have an option for topography optimization. So what is topography optimization is? In this we can optimize the shape of the component under the given loading condition. Okay, so topography optimization we'll be discussing later. For this tutorial we'll be doing topology optimization. Okay, so we can go inside topology by clicking on this and then we'll go to create. Okay, so I already have created a variable named weight here. Okay, as you can see in this white browser area. So how you can create this variable is under the design variable. You will name this design variable. I've named it weight. You can name it something according to your wish. Okay, so I've named it weight. Okay, then we have to select the property type which will be modified. Okay, so the property type here is p-solid, as the property which we have created for the design and non-design part, both are p-solids. Okay, and we have to select the property which will be modified here. So I have selected the design property under this. We go out and if we see here, so if you go to this weight component here, you can see I've selected the property type as p-solid. Okay, and we'll select the design property to be modified. Okay, so after that, topology. After creating the topology design variable, we'll assign some parameters to this variable. Okay, so the minimum dimension which should be there of this for this design variable, we have kept it as 12. Okay, for this tutorial I'll explain it in some upcoming video why we do this. Okay, then pattern grouping. So for pattern grouping, we have used a 2-plane symmetry. Okay, so you can just select 3 nodes on this plane and it will apply this pattern grouping. Okay, so going back, the next variable which we need to create next is responses. Okay, so what are responses? So basically responses are how will the optimizer or the solver which is running the optimization will respond to the given loading conditions. So I have created 2 responses here. You can see here. So it's here in the white browser area. I've created 2 responses, optimization responses. One is weight response, one is volume response. So what will weight response do is it will reduce the weight of the component, whereas what is volume response do? It will optimize the volume of the component. Okay, so under weight response we have to select the load step also. Okay, so we go to the load step, we'll select static analysis here, which we have created the load step static analysis, and then we'll return. And for volume response, we have selected volume fraction. Okay, for this we don't need to select any load step. Okay, so these are the 2 responses which I have created. Okay, so these responses, what do they do? So these are the responses which the optimizer or solver, whatever you say, it provides under these loading conditions. Okay, so after this we need to create some constraints. So what are these constraints? So constraints are basically the limiting factor up to which the optimization can be done. So we'll tell the solver or the optimizer, whatever it is, that okay, so this is the upper bound or this is the lower bound up to which we can go. So basically I have given here upper bound of 20%, as you can see 0.2. Okay, I have named this as volume constraint, and the response I have put is volume response. So what will happen? The volume here won't reduce below 20%. Okay, 20%, at least 20% will be retained. Okay, so the constraint is placed on the volume response. So I've already created a volume response. If you can, yeah. So it's here in the white browser area. So volume constraint, as you can see, it's 0.2, upper bound is 0.2. Fine. So we have created the topology design variable. We have created the responses, weight and volume response. We have constrained the volume response up to 20%. Okay. So next we'll be creating the objective of the response. So what is the objective of the response? So our objective of the response here is to reduce the weight of this component. Okay. So what we'll do, we'll select minimum here. We have options for maximum also here, as you can see. But since we are reducing the weight, optimizing it for the least weight, we will select minimum here. The response type will be weight response. Okay. So I have already created this objective here. So as you can see, one objective is already created. Okay. So it will be a weight reduction objective. Okay. So what all variables we need to create for optimization is we need to select the appropriate optimization that we are doing. So in this case, it's topology. So we have created a design variable for topology optimization. Then we need to select the responses, that what type of responses will the solver give. So the solver will give us volume and weight response in our case. So, and then we need to select the constraints on either of the responses. Okay. So we have constrained the volume. That volume can't go below 20% of what it's there. So that is the constraint. And then we have to select the objective, that what we want to do. We want to increase, we want to decrease weight or volume, something like that. Okay. So now we are all set. Check it from the starting. So we have a mesh model. We have applied boundary conditions here. We have created the topology design variable. We have created the objective. We have the optimization constraint. We have the optimization responses, and we have created and assigned the properties to the components. Okay. So we are all set to run. Okay. For running the optimization, we need to go to analysis. We need to go to Optistruct, and here there will be little change as compared to previous analysis that we have done. The export options will be all as usual, but the run options, if you remember previously, we used to select analysis under the run option, but here, since we are optimizing the design, we will select optimization here, and the memory option will be default. Okay. So then we'll click on Optistruct and we'll run the optimization. So once you run the optimization, a pop-up window like this will appear, as you can see here, and it will show the progress of the optimization under optimization summary. As you can see, it's started to optimize. It will run through several iterations. I scroll here. So you can see here iterations of case, it's 0, 1. So it will run through several iterations so that it can converge to a feasible result. So if the modification or optimization of this design is not feasible, then it will print that under the given constraints it can't be optimized. So we'll see if this bracket is optimizing under the given constraints. It's infeasible. So we'll get to know this in a while. So we'll wait for this to complete. See progress is 6%, iteration progress 27%. which iteration we are in? We are in fourth iteration. We are in fourth iteration. So this will take some while to run. We'll fast forward to when it's completed. Okay, so the run has been completed and we have the model here in Hyper-V. Okay, so as you can see here, the component is here and the element density is plotted here. Okay, so this is one, as in this will be complete. There won't be any modification here. Okay, so this red area will be complete. So this is the model in iteration 0. So we can see here how many iterations it has done. So we can go here in the drop down and we can go down. So iteration 0, 1, 2, 3, 4, 5. So it has gone up to 28. Okay. So if we see currently we are in iteration 0, so we see how it's looking in iteration 4 suppose. Okay. So as you can see, it will be something like this in iteration 4. Okay. So to see how the bracket will look like in the iteration 4, how it's optimized, we can go to ISO here, as you can see, which is beside Ubuntu. So we go to ISO, okay, and then select the component, display, and we click on apply. Okay, so as you can see, in iteration 4, the solver gave a solution something like this, but this isn't a good solution, I would say. So we'll go further to further iterations and we'll see the code will go to iteration 24 here. Okay, so how it's looking here, we'll see. We'll again go to ISO and click on apply. Okay, so this looks a bit better. There's connection between these holes and this, which was not there in iteration 4. Okay, so it's looking a bit better. Then we'll go to iteration 28. Okay, so iteration 28 is also very similar. There's a slight change. So you can see the unnecessary mass which was there, which didn't contribute to any stiffness of the bracket, was removed under the given boundary conditions. So this is the this is the mass and the volume of the bracket which are sufficient under the given boundary conditions. Okay, so what you can do is you can try out yourself with some components of your choice. You can follow the same steps which I have followed for optimizing the design of this bracket component. You just have to divide the component of picture into design and non-design areas, and then mesh it and apply the properties, materials, and the boundary conditions. And after that, you have to create the topology design variable, response, constraints, and objectives. Okay, so try it out and tell me how it goes. Okay, and comment in the comment section. So this will be all for this video. In next video, I'll try to cover the topology optimization. Okay, so if you got to learn something new from this video, please like, share, and subscribe. And don't forget to follow my Facebook and Instagram page, where I post regularly about analysis and optimization and some things which we can do about Hypermesh, some tweaks, some tricks, some tips on Hypermesh. So yeah, that's all. So this is all for this video. Hope you like this video. Please share, like, share, and subscribe. Thank you.